Good morning, students. Today we are going to see Introduction to Thread Specifications for the subject MEE 2001 Machine Drawing. So I am Dr. R.A.K. Selvakumar, Associate Professor Senior in the School of Mechanical Engineering, Assistant Director Placement and Training in Vellore Institute of Technology, Chennai, Tamil Nadu, India. So last class we have seen the thread specifications. The first one we have seen in the last class is thread forms. So in this class we are going to see the remaining things. So first we are going to start with thread series. So BAS recommends two thread series, coarse series and fine series, based on the relative values of the pitches. So pitch is considered as a major parameter in this thread series. So, however, it must be noted that the concept of quality is not associated with these terms. For any particular diameter, there is only one largest pitch called the coarse pitch, and the rest are designated as fine pitches. So for any particular diameter, there is only one largest pitch called the coarse pitch, and the rest are designated as fine pitches. So diameter pitch combination for ISO metric threads are given in this table. So I'm going to brief about this table. So you can see nominal diameter is there and the pitch values are there, and in the nominal diameter they have divided into two categories, first choice and second choice. The first choice you can see that it is starting from 2 to 300. In the second choice it started from 2.2 to 95. So these are the various nominal diameters given by ISO for various metric threads. So next one is in the pitch you are having two category. One is coarse, in that it is starting from 0.4 to 6, and another one is fine, and it is the fine pitch is having three categories. One is starting with 0.25 for the nominal diameter of 2 mm2. The fine pitch value is 6 for the nominal diameter of 300 mm. And the second class of the fine pitch, it is starting from 0.5 to 4 mm for the nominal diameter of 6 to 300 mm. So coming to the third class of the fine pitch, it is starting from 0.75 for the nominal diameter of 10 mm, and the maximum is 3. The value of the pitch is 3 for 300 nominal diameter value. So next one is after the thread series, the another specification in the thread is thread designation. So the diameter pitch combination of an ISO metric screw thread is designated by the letter M. So followed by the value of the nominal diameter and pitch, the two values being separated by the sign cross. So for example, a diameter pitch combination of nominal diameter 10 mm and pitch 1.25 mm is designated as M10 cross 1.25. If there is no indication of pitch in the designation, it shall mean the coarse pitch. So if suppose they have given only M10, that means there is no indication of pitch in the designation, so it shall mean the coarse pitch. This is the thing. So you have to take in the coarse category only. For example, if I give only M10, then you have to take only the coarse pitch, the value is 1.5. If it is 20 in the nominal diameter of the first choice, then you have to take 2.5. Yeah, for example, M10 means that the nominal diameter of the thread is 10 mm and pitch is 1.5 mm. Next one is thread designation. Following are the other designations depending on the shape of the thread profile. So SQ 40 cross 10 means square thread of nominal diameter 40 mm and pitch 10 mm. So here SQ stands for square thread. Next one is Acme 40 cross 8. So Acme thread of nominal diameter 40 mm and pitch 8 mm. So warm 40 cross 10 means warm thread of nominal diameter 40 mm and pitch 10 mm. So all this square, acme, warm, the thread forms we have seen in the last class. So next one is thread class of fit. So various classes are there in the thread. So there are three classes of fit established by ANSI for general use. So designated 1, 2 and 3. The classes indicate the tolerance or tightness of fit between mating threaded parts. So the classes indicate the tolerance or tightness of fit between mating threaded parts. Don't you have to understand. So class 1, if they define means, so a loose fit where quick assembly is required and looseness or play between parts is acceptable. So in any kind of a thread, if they mention class 1 means it's a loose fit where quick assembly is required and the looseness or play between parts is acceptable. So class 2, a high quality general purpose commercial class of fit for bolts, nuts and screws, widely used in mass production. Class 3, a very high quality threaded fastener with a close fit used for precision tools and for high stress and vibration applications. So based on your applications or based on the industry needs, we can clearly define the thread whether it is coming in a class 1, class 2 or class 3. Further, you can refer to the Machinery's Handbook, Table 4, Screw Thread Systems for the actual upper and lower limits of each class of fit for a particular thread. So next, the single start thread. So a single start thread consists of a single continuous helical groove for which the lead is equal to the pitch. Diagram shows the single start thread. So you can see the lead which is equal to the pitch. So single start means the lead is equal to the pitch. So you know what is lead, what is pitch, which one was explained in the last class in the screw nomenclature. So as the depth of the thread depends on the pitch, greater the lead desired, greater will be the pitch and hence smaller will be the core diameter. So which reducing the strength of the fastener. So to overcome this drawback, multi-start threads are recommended. So multi-start thread. In multi-start threads, lead may be increased by increasing the number of starts without increasing the pitch. So you can see the diagram. So the lead is increased without increasing the pitch based on the start. In double start, so you can see the lead is increased than the pitch. For a double start thread, lead is equal to twice the pitch. In double start threads, two threads are cut separately, starting at points diametrically opposite to each other. So if you see the sketch, the color variations shows it's a two threads are cut and starting at points diametrically opposite to each other. In triple start threads, so this is the triple start threads. It is also on kind of a multi-start thread. The starting points are 120 degree apart on the circumference of the screws. So the starting points are 120 degree apart on the circumference of the screws. And you know very well that for a triple start thread, lead is equal to thrice the pitch. So it's a lead, this is the pitch, and you can understand that. Multi-start threads are also used wherever quick action is desired, as in fountain pens, automobile starters, arbor press spindles, hydraulic valve spindles, etc. So next one is right hand thread. So screw threads may be right hand or left hand depending on the direction of the helix. So if you see the diagram, right hand threads are advances if you are turning clockwise. So if you see the thing, a right hand thread is one which advances into the nut when turned in a clockwise direction. So if you see the diagram, so it's advances direction. So if you are turning in a clockwise direction. So left hand thread. So if you see the diagram, you'll come to know that it will advance to the nut if we are turning counterclockwise. So a left hand thread is one which advances into the nut when turned in a counterclockwise direction. So this advances, so you have to turn into counterclockwise. An abbreviation LH is used to indicate a left hand thread. Unless otherwise stated, a thread should be considered as a right hand one. So please make a note of it. So if it is denoted as LH, then only it's a left hand thread. Otherwise, it should be considered as a right hand thread. So next one is representation of the thread. How to represent. So if you see this particular values M6 cross 1 hyphen 4 H 5 H. So this is the representation of a screw thread. This is also one of the important specifications of a thread. So here I am going to explain the internal thread, particularly right hand. So M denotes thread form symbol. So this one we have seen the last class, thread form. The next one is the 6 denotes nominal size in millimeters. So this numerical value is the nominal size in millimeter, the nominal size of the thread. Next one is this numerical value denotes pitch in millimeters. So after the hyphen, this 4 denotes the tolerance grade. The capital or uppercase letter H denotes tolerance position, and the 5 denotes tolerance grade, and the H, capital H, denotes tolerance position. So all these 4 parameters are coming under tolerance class. So next one, from the left end, the first and second from the left end denotes crest diameter of the tolerance symbol. And from the left end, the third and fourth denotes pitch diameter of tolerance symbol. So the crest and pitch we have seen in the last class. So this is the way we have to represent a internal thread. So here I mentioned as a right hand. So you should know what is thread form and a numerical value which says the nominal size of the thread and the pitch value of the thread and tolerance position and tolerance grade of the pitch diameter, tolerance symbol, and tolerance position, tolerance grade of the crest diameter, tolerance symbol. So next representation. So if you see this, it's similar to the previous one, M6 cross 1 hyphen 4. So instead of uppercase letter, there is a lowercase letter H, 5 H. So it's an external one. So it's again M is the thread form symbol. So 6 is nominal size in millimeters, good. And 1 you know very well, it's a pitch, very good, in millimeters. And 4 denotes tolerance grade, so it's need not to be 4, it should be a numerical value. And H should denote the tolerance position, it should be in a lowercase letter. And 5 should be the tolerance grade, again it's a numerical value. And the symbol should be a lowercase letter and it's a tolerance position. So as said in the previous slide, All these things are, four things are coming under tolerance class. So the last two denotes crest diameter tolerance symbol. So in the tolerance class, first two denotes pitch diameter tolerance symbol and symbol. So the variation compared to the internal and external thread is the uppercase and lowercase. So external means lowercase letter in the tolerance class. Internal means uppercase letter in the tolerance class. So next important thing is conventional representation of the screw threads. So if you see the diagram, the first one is an external thread, and how to denote that is given in the right side. The arrow indicates that how to conventionally represent a thread, and it's an external thread. So it is without section. So if we come into the next diagram, it's a sectional view, and it is having a thread externally, and also it's having two holes in the center with various diameter. So you can see that hole, and also clearly mentioned there. If we come to the third diagram, so it shows the sectional view and also without a section, and the center one denotes the side view of these two, and the internal thread how to specify in conventionally is clearly given in the center. The arrow indicates how to conventionally represent a thread in the side view. So next diagram shows clearly that compared to the third diagram, the fourth diagram is it is having a hole and also a thread. In the third diagram, if you see that it's a through hole and it is threaded, the sectional view and without section. The views are giving clearly the front and side view. One is section, another one is without section. But if you come to the last diagram, there's a fourth one, so it clearly says that it's having a hole and a thread, internal thread, and it's clearly the side view is given in hidden lines, and the thread is clearly represented in the diagram. So the fourth one is a hole with the internal thread. So this is the way you have to represent the internal thread with the hole. So the first one is, if you see, it's not sectioned. The front view and left side view you can see. So it's external thread. You can see in the left side view, it's clearly mentioned. The inside is not a circle, it's a curve. The outside one is a circle. So this is the way you have to represent the external thread. So coming to the next one, it's a sectional view. By seeing itself you can understand, and you can see that it's an external thread, and also it's having two different holes in the center. So the thread is clearly represented in the front view and also in the left side view, and also the hole is also clearly represented in the diagram. So two various holes clearly mentioned. So if you come to the internal thread, so you can see that there is a sectional view, and without section also it's clearly given the left side, and you are having the side view, and the side view clearly says the inner diameter is a circle and the outer one is a curve. So this is the major difference in the representation of a screw thread in the, if it is having an internal thread. So external thread means, you can see here there is a outer one is a fully circle and the inner one is a curve. So if you come to the internal thread, you can see clearly that The inner one is a circle and the outer one is not a circle, it's a curve. So the same thing is explained in the next one. What is the difference between the third diagram and the fourth one? Is the third diagram, it is actually through hole, and it is after the through hole it is threaded. But if you are coming into the fourth sketch, you can see that one is sectional view, another one is without section, and the side view is there. You can clearly see that there is a hole, after that there is a thread. So two things are there in the fourth diagram, and also how to represent also clearly given in the side view and the front views. So next one is the schematic representation of the V thread. So just focus there. So this is the way when you are representing a V thread, you have to draw lines in machine drawing. So you can see that it's external thread, so you have to clearly specify. So one is the nominal diameter is clearly visible in the outermost circle, and the threaded portion, it's a curve, it's not a circle when you are representing a thread. So coming to the next diagram, if you see that the internal thread with the hole is clearly specified. So front view, and then you are having a right side view. So next one is, it's a through hole and it's threaded. The difference between the second and third diagram is the second diagram has a hole and a thread, internal thread. The third diagram have a hole which is through hole and it is threaded. And the arrow indicates how to schematically represent the V thread in the side. So next one is schematic representation of square thread. So you can see the diagram, one is external, another one is internal thread. So this way you have to clearly draw the or represent the square thread single strand. And in the side view, it's a left side view, similar to the earlier slide. So you have to clearly specify the square thread. The next diagram is internal thread. It's an internal square thread. So the difference between external and internal, how to represent, you can understand, it's quite opposite. It's like a mirror. The threads are just opposite when you are mentioning the external and internal. And also you can see the representation in the left side view. The internal thread should be clearly represented like this. So external and internal threads in engagement. So if we see this diagram, it's how to represent conventionally and schematically. We will understand much better. So you see this is the representation of external and internal threads in engagement. It's a schematic representation. So if you see this particular representation, it's coming under a conventional representation of external and internal threads in engagement. So it's a schematic. A is a schematic representation, B and C says that it's a conventional representation. So references for this particular lecture, it's similar to the previous session. Technical graphics communication by Gary and machine drawing by Narayana. So dear students, please stay home, save lives. Thank you.